Yeah, all right. So our next speaker is Nolan Matthews, who will be telling us about intensity interferometry at Calern and beyond. So please take it away.
Okay, thanks, Dan, for the introduction. So yes, I'm Nolan Matthews. I'm a postdoc at the Institute of Physics in Nice. I've been doing work in intensity interferometry at Calern and recently trying to go beyond. Before I begin, I just want to thank the organizers for giving me time for this talk, and also just thank the organizers for organizing such an exciting conference. As someone who's not deeply embedded in this community, it's been like really fascinating to learn about all the different science that's now being done with modern facilities and what will be done with future ones as well. The clicker is not working. I'll just use this. So I think many of you have heard of the technique of intensity interferometry, but maybe are not so familiar with it in detail. And so just as a quick primer, I wanted to go over the technique itself. In principle, it's kind of simple to describe. We have two telescopes in interferometer, which are separated by some projected baseline B. Let's say we're observing a star with some angular diameter theta. The main idea of intensity interferometry is that we record the intensities at the two different telescopes, and then by correlating them after accounting for the optical path delay, we're actually able to probe the squared visibility through this relationship at the bottom. Oftentimes, this normalized correlation function is referred to as G2, it's the language of quantum optics community. And again, by measuring this at zero optical path delay, you probe the squared visibility. To give you a picture of what that might look like, I plot here on the left the intensity as a function of time for different baselines, and where the different colors represent what the different telescopes might see. And what you see is that as you make the baselines larger and larger, the intensities begin to decorrelate. To quantify this correlation, we form a correlation as a function of the time lag. And what you see is that at zero time lag, zero optical path delay, you get an excess of correlation. And as you go to larger and larger baseline, this correlation dies down. The peak, the amplitude of this correlation is the term that's proportional to the squared visibility. And so by tracking the amplitude of this correlation with the baseline, we can then of course fit visibility models and extract spatial information about the source. The caveat is that the coherence time, the time scale in which these intensity fluctuations are correlated, is very short. And for optical light and reasonable bandpass, it's much less than a picosecond. And so what this does is reduce the contrast of the peak that we see, the correlation peak, and degrades ultimately the sensitivity. But the flip side of that is that you've now reduced your tolerance or your required precision in the mechanical system to the corresponding light, the path length for the equivalent light travel time. So for example, if I record my system with 100 picoseconds, then I only need to keep my mechanical precision to better than say 3 centimeters. And what this means is that effectively the technique is insensitive against atmospheric turbulence, can then operate at short optical wavelengths, can be scaled to long baselines. And because it requires only the intensities, you can record, let's say, the photon arrival times of different telescopes. This makes it able to scale to many different telescopes quickly. This fact is also allowed for its use and realization in large light bucket shrink-up telescopes. In fact, the work of my PhD thesis with the Veritas array. This was realized in 2006 by Kuglo Leboeck and Jamie Holder. And now recently, all major IACT arrays, MAGIC, Veritas, and HESS, are pursuing intensity interferometry observations. You can also see Dave Kita's poster for that. So I think one of the biggest criticisms of intensity interferometry is the sensitivity. And so I just wanted to kind of briefly go over that. On the top left, I'm plotting the sensitivity, which is the signal to noise of the intensity interferometer as a function of various different instrumental parameters. You have the telescope area, the global light collection efficiency, the time resolution, which you want as fast as possible. But another unique aspect of intensity interferometry is that it's independent of the optical bandwidth. And what that means is that you can split your light into, say, 100 different spectral channels, and then measure the intensity correlations between each spectral channel, and then co-add them to ultimately improve your signal. And what you see is on the right, what I'm doing is I'm plotting the relative error in the squared visibility as a function of the visual magnitude for a 1-hour observation, global light collection efficiency of 30%, and a partially resolved source, the visibility of 0.5. What you see is that for a single spectral channel and let's say 500 picosecond resolution and a 1.5 meter telescope, you're quite limited in what you can do. But as you push the time resolution, let's say down to 50 picoseconds, and expand the number of spectral channels, you really can start to push. And again, you can do this at very short optical wavelengths. So even with a 1.5 meter telescope, thanks to YouTube for building the narrowbody instrument, which was 6 meters in diameter, with a 1.5 meter telescope, you can get down to magnitude 4 or 5 in just an hour observation. Ultimately, we'd like to do this on a very large telescope. When you've got an 8 meter telescope, you can then push even further to beyond 8th visual magnitude. Natively, the technique is best suited for hot stars, so the OBA type stars. And what you can see just within, I don't have the time to go into all the independent science cases I think would be interesting for an interferometer, but there's hundreds of cases. In particular, this is the number of stars in the Bright Star catalog with a declination greater than -20. And so there's, I think, lots of interesting science cases, many of which have been talked about here, but studies of massive stars interacting binaries, in particular, studies of massive stars like Wolf-Rayet stars, LBVs, BE stars, and the studies of emission lines. And just as an example, this is an example spectra of P Cygni, in which case, if you look towards the blue, you have, of course, you have H alpha, which is very well studied in interferometry, but you also have many other hydrogen and helium lines, which you could potentially study. So this kind of led to a consortium, a collaboration between the InfiniE cold atom team, which are Calern optics experts, actually study light atom interactions in cold atom systems, and they use intensity interferometry to study these systems. And they formed a collaboration with astronomers from the Observatory Côte d'Azur, and as well from the metrology team from JOAZUR. This has led us to using the facilities on the Calern Plateau in southern France, which is probably very familiar to many of you. And in particular, we've been using the C2PU Observatory, which is a pair of 1 meter telescopes separated by about a 15-meter baseline. More recently, we've expanded our ability to do interferometry onto the Mayo telescope, which is shown on the top left there, which is a 1.5 meter telescope used for laser ranging, and as well even to the T1M telescope, which is a portable 1 meter telescope, and in fact can be packed up and put into that trailer, as well as moved to different baselines. And so on the map on the bottom left here, I'm showing you the positions in which we have a very precise location, and we plan to be able to have modular baselines in that case. What exactly does our setup look like? This is just kind of a illustration of the setup. The main idea is that the focus of each of the telescopes, we have a coupling assembly. And what this does is do spectral and polarization filtering and then injects the light into a fiber. I don't have time to get into too much of the details, but the main idea is that you have a tip tilt, which helps stabilize the light injection into the fiber. The light is collimated. We have a guiding camera which has a control algorithm to keep the light injected into the fiber. And then we do the spectral and polarization filtering. After the light's injected into the fiber, we split the light in each spectral/polarization channel in order to measure the G2 value for 0 baseline correlation. And then by measuring the correlation between telescopes, we can normalize by this 0 baseline correlation in order to obtain the squared visibility. Our detectors are using exolitas detectors, which have roughly 700 picosecond timing and quite good quantum efficiency for a wavelength of interest. And then we send the signal from the detector to a high-speed TDC, time-to-digital converter, in which case we have 10 picosecond bin size, and this performs a real-time correlation. This system has been progressing significantly over the last few years. It started in 2017 with observations with C2PU, in which we measured the 0 baseline correlation on 3 different stars. This then expanded to performing intensity correlations between the 2 telescopes, which is shown in the bottom left. And more recently, we've been able to do distant calibration to P Cygni as well to Rigel using a combination of intensity interferometry to obtain the angular diameter and spectroscopic modeling. More recently, we've gone beyond just using C2PU, and we started to use Mayo and the T1M portable telescope, and that's what I'm showing in the top left here. So Mayo is in the background, T1M is in the front, and you can actually see the coupling module on the T1M telescope right here. And in these observations we performed in January 2022, we observed gamma CAS in its H alpha emission line. And so with the observation of H alpha, we were able to see very clearly a strong 0 baseline peak, as well as, and then we moved T1M between intermediate and a long baseline to observe the reduction in contrast. The analysis is still impending, so we know a lot of other stuff as well. But one interesting aspect is that we're able to to match the 2 telescopes, which are different optical designs. We have Dobsonian and one Coude-Naismith design. And so on the Mayo-Naismith bench, we incorporated a rotation stage, which allows us to rotate the polarizations to be aligned in the 2 different telescopes. And a very exciting recent observation was we were granted opportunity to perform technical tests with 2 of the VLTI AT telescopes while they were separated while they're at their maintenance stations, separated by 49-meter baselines. This occurred while the delay lines were in use for the UTs. And so the main idea is that there's really no impact on ongoing programs. And it's really key for us. To do this, we introduced a removable dichroic in the beam path just before the Naomi adaptive optics system and a modified coupling assembly, which you can see in the center there. And during this campaign, just last month, we observed a single telescope bunching peaks on 3 stars and then measured the cross correlation between 2 telescopes on 1 star, as just shown on the right. So big thanks to Peter Bourget and Nicolas Schuler, who were essential in helping us install our equipment. You can see, as I said, a picture of the coupling assembly here. I believe it's called the Ross right here, which is sending the signal through the optical fibers to the detectors. And just to comment, we packed up all our stuff from France, sent it to Paranal, and packed it into these suitcases here, and then brought it back in at the end of our observations. We really transported a stellar interferometer and then brought it back with us. I'm not sure how much time I have. 2 minutes? Okay, perfect. So, and so we've demonstrated so far the ability to adapt our system onto different telescopes. But of course, as I mentioned, to really make intensity interferometry an attractive technique, you need to push the time resolution and push the ability to do multispectral channel, at least when using optical telescopes. And so in the laboratory, we've been working towards a system in which to test these multi-channel observations. What we do is we inject light into a single mode fiber, thermal light into a single mode fiber to create a point-like star. This light, we conjugate the image on the output of the fiber into a spectrograph. And at the output of the spectrograph, re-inject back into a fiber. And using our setup so far, we were able to inject the light back into the fiber and observe the bunching peak at the output. And effectively, I didn't get into the details, but the amplitude of this is at 10 times higher because the bandpass is much, much smaller. And so you can see a much higher peak. And in fact, we get away from all the noise of the electronics by using optical path delay, but also because the peak is amplified by the narrower spectral width. A unique aspect is that if you had such a thing on sky, you could actually rotate the grating to some wavelength of interest. And in the near future, we're going to be doing tests in which we want to do multiple channels in parallel by using a fiber array in conjunction with B groups. So in summary, I believe that intensity interferometry with modern high time resolution detectors paired with optical telescopes offer really great potential for high angular resolutions at visible wavelengths. Particularly, I think this is for the U, B, and V bands to help complement existing programs. In particular, the specific science cases, I think, are studies of massive stars, including interacting binaries, Wolf-Rayet, BE, LBV systems, in both the continuum as well as in emission lines. As I mentioned, our system is really adaptable and modular. We can adapt it to telescopes of different optical designs. And in principle, any optical telescope array could be used for intensity interferometry, given access to a telescope focus. In the future, we're going to continue our programs with Calern and the VLTI, hopefully extending to 3 and 4 telescope observations, continue our development of multispectral channel capabilities. The mic. And another exciting thing we're doing is to perform tests with superconducting nanowire single photon detectors, which have very, very good quantum efficiency and extremely good time resolution. So with that, I'll leave you with these nice pictures of keep dropping my mic, of the facilities at Calern, and I thank you for your time.
Hey, thank you for that very interesting talk. Do we have any questions? Yes.
I have 2 questions. First, since the method is just to record intensity and then do some computing, then does it still matter whether the telescopes have same dish size? For example, can we use one 8
No,
meter?
you can use telescopes of different optical designs or different dish sizes. It's fine. I mean, it's only a factor when your dish size starts to become an appreciable fraction of the resolving baseline. So for example, if you're looking at large sources and you have a 20-meter telescope, you might partially resolve the source. But if you have a 1.5-meter telescope or a 10-meter telescope, but you don't significantly resolve the source, there's no issue in that. And so you have, of course, a difference in the flux, and that affects the sensitivity, but it doesn't prohibit the use of the technique, if that's the question.
Another question. So what cadence of recording is needed for this tool?
Cadence?
Cadence, okay.
So I didn't get into the details of how the observations are done. Essentially, we record a correlation approximately every 1 or 5 minutes. And then we record a series of these cross correlations over the entire observation, and for these observations, because we're using small telescopes with single channel, lasts tens of hours. But to correct for the optical path delay, what we do is we shift all these correlations with respect to each other in time, and then we can just co-add the different correlations after we've accounted for the optical path delay. maybe that's,
Thank you.
Okay, and we'll just take one question from online. How many channels would be possible with superconducting nanowires?
yeah, so we started a nice collaboration with scientists at the Delft University in the Netherlands. And so right now they have systems which you can, so it's at the moment you can only couple a few. And it's because being able to couple 100, we're coupling into 100 micron diameter core graded index multimode fiber, and these aren't entirely compatible with the current generation of superconducting nanowire single photon detectors, but the people in Delft are working on these multi-mode coupled ones. At the moment, I think you can only couple several, but we're trying to think about ideas to be able to do maybe free space, having a multi-pixel detector and able to do spectrally disperse it onto the detector in free space, instead of having a fiber for every single spectral channel.
Yeah, interesting stuff. All right, can we thank our speaker again?
Thanks.